Hi everybody. Today we're going to talk about the ideal gas law, and the ideal gas law is defined as this. The pressure times the volume of any gas is equal to the number of moles of that gas times a constant R that we'll define in a second times its temperature. So I think now might be a good time to point out that on your whole year resources page, on the lower right hand side of the back, there are a whole bunch of equations, this entire box, that relate to gas laws. So today, we're going to focus our attention on this ideal gas law. And I also want you to notice that there's some more information down here in the box on the bottom. Down here at the bottom where it says ideal gas constant, there are some values for this constant R that we just talked about. So that's the R in PV equals nRT. And also notice that STP is defined. So remember, we said STP means standard temperature and pressure. Standard temperature is 0 degrees Celsius, standard pressure is 1 atm, and it turns out that if you have any gas under those conditions, 0 degrees Celsius, 1 atm of pressure, if you have 1 mole of any gas, it always occupies the same volume, 22.4 liters. So we can use that to our advantage whenever we want to figure out what this R value is in PV equals nRT. We're first going to solve PV equals nRT for R. So if we want to do that, we have to divide both sides by NT, get R on its own, and so we get PV over NT is equal to R. Let's now plug in those values at STP. So we said STP is 1 atm. It's 0 degrees Celsius, which in Kelvin, because we always want Kelvin for gas laws, is 273.15. The volume we said is 22.4 liters, and that is the volume that 1 mole of any gas always occupies at standard temperature and pressure. And so if you do that math, if you figure out what R is equal to, it's always equal to this value, 0.0821 liters times atmospheres over moles times Kelvin. So a few things about this. Number one, the units are crazy, right? We need to make sure that we include these units every time we use R. You'll see why that's important in a second. This also means that if we're defining R as a value at STP, whenever we plug in variables in an equation, we're basically comparing those variables to what would happen at STP. So at STP, we know 1 mole of a gas occupies 22.4 liters. Let's change some of those variables and let's see what happens in relation to STP. So let's dive in with our first real gas law problem, and it turns out that there are a few things we want you to do when you encounter a gas law problem. And the first of those is to read the question and to define your variables. So you'll notice in number 1, it says, what is the pressure? So we know that P is a variable that we're interested in, and what is it? Well, that's our question mark. What is the pressure exerted by a 0.5 mole sample? So 0.5 moles. Remember above we said that N is equal to the number of moles. So this is 0.500. Keep your sig figs. It says we have a sample of nitrogen gas in a 10.0 liter container. So liters, what is liters? Well, liters is a volume. So our volume is 10.0 liters. And it says we're at 298 K. So our temperature then is 298 K. Now we're on the ideal gas law note page, so chances are we're using the ideal gas law. But there will come a time very soon when we don't tell you which gas law to use. And this is how you figure out which gas law to use. You look at your list of variables, figure out which gas law would apply, and you'll notice that the gas law that says PV equals nRT has all of those variables that we just defined and isn't missing any. So it does have one unknown with it, which is the P, but because R is a constant, we know every other variable. So if we want to solve this thing for P, let's do that. Let's show our work. So if we want to solve for P, we have to divide both sides by V. We'll get P is equal to nRT over V. This is worth points on your test. So defining your gas law is worth points. You don't have to write the name ideal, but you have to write out the gas law that you're using. And remember, those gas laws are things that are provided to you on the whole year resources. So you're basically picking out one of these gas laws over in this box. We're, of course, using the ideal gas law right now. And then you have to show your work to rearrange for the variable you're solving for. So we said we want to solve for P. That's why we've rearranged for P. It's also worth points to show plugging in to this equation. So we said that we're solving for P, and that is equal to N, which we said was 0.500 moles, keep your units, times R. R is a constant. R is 0.0821 liters times atmospheres over moles times Kelvin, times temperature. The temperature that was given in the problem is 298 Kelvin. And we are putting that all over volume. So our volume, we said, was 10.0 liters. And when you've done that, check out what happens with your units. So you have, in the numerator only, a moles on top and moles on the bottom in the numerator. You have a Kelvin on top, you have a Kelvin on bottom in the numerator. You also have in the whole fraction a liter on the very top and a liter on the very bottom. So the only thing that's left uncanceled is ATM. We're solving for a pressure, so it's good that ATM is left uncanceled, and when you solve for that pressure, you will get, with correct sig figs, 1.22 ATM. And in terms of significant figures, the fact that we made our list actually makes our life really easy, because if you go down your list, you check for the sig figs involved. So pressure we're solving for, N has 3 sig figs, volume has 3 sig figs, temperature has 3 sig figs. That's why our answer at the end of the day had 3 sig figs. All right, let's try another. Define your variables first. So in number 2, it says, what is the volume? So our volume is now the unknown. What is the volume of a 0.250 moles? So moles is N. Keep your sig figs, 0.250 moles. So 3 sig figs there. And we are told it is at 20.0 degrees Celsius. So T is 20.0 degrees Celsius. But remember, temperature must always be in Kelvin for gas laws. So let's take care of that right now. To get to Kelvin, we have to add 273.15. So let's add in 273.15. 20 is significant to the ones place, so we'll make our answer significant to the ones place. When we do that, we get 293.15, actually significant to the ones place, tens place, 293.2 Kelvin. So you can do that conversion right in the list like we've done. And then finally, we are told that we have a pressure of 740 with a decimal point, mmHg. So you see your variables, you need to figure out what to plug in. When you go to plug in, you'll notice something, right? So let's define our gas law. It, of course, is PV equals nRT. We are looking to solve for volume. So to get volume by itself, we have to divide off pressure. So we get nRT over P. But if you plug in, remember R has units right here. R has units of liters times atmospheres over moles times Kelvin, right? The pressure that we've been given is in mmHg. So mmHg and the atmospheres in the R value that we have are not going to cancel. So we have some choices. Let's first try the more roundabout way. So let's convert this pressure that's currently in mmHg into atmospheres so that we can use it, right? So 740 mmHg, we know that there are 760 mmHg in 1 atmosphere, 1 ATM. We started with 3 sig figs. When you do that math, you will end up with 0.974 ATM. And now you have a unit that works. So let's plug in, right? We have a volume that we're trying to solve for. We know that we have 0.250 moles of this gas. We know our R value because R is always 0.0821 liters times atmospheres over moles times Kelvin, times our temperature. Our temperature, we said, was 293.2 K. And then we're going to put all of this over our pressure. And our pressure that we just converted turns out to be 0.974 ATM, right? And so now if you look at the numerator, you have moles on top, moles on the bottom, Kelvin in the bottom, Kelvin on top, ATM in the very top, ATM in the very bottom. You're left with liters. Liters is what you want to be left with because you're solving for a volume, and you end up that your volume is equal to 6.18 liters. You have 3 sig figs. If you look back to the beginning of the question, you started with 3 sig figs, right? So that works, and that absolutely is a good way to do this. But there's a bit of a shortcut we could have taken, right? So I showed you that R had a problem because our units of pressure didn't match. We started off with units of pressure in mmHg. But if you go back to your whole year resources page, there's a pretty tricky little thing going on with R values. So you'll notice in R values, moles times Kelvin is always the denominator. Liters is always in the numerator. But the pressure can change, and if the pressure changes, you'll notice you'll get a different R value. So basically we have 3 different R values that will allow you to use, and they all have different units of pressure. So we can make our lives easier by selecting this R value that already has mmHg because our unit is given in mmHg. So it's 62.4, right? So we could have, you don't need to show both ways, I'm just showing you how you could have done this. We could have, when we had V equals nRT over P, we could have plugged in our V is equal to our moles, which was 0.250 moles, times that R value, which was 62.4, liters times mmHg over moles times Kelvin. And then this is multiplied by, I've run out of room, I apologize. So this is multiplied by the temperature, which we said was 293.2 K. My apologies for the sloppiness here. And then we are putting that all over the pressure, but in this case, the pressure doesn't have to change. So we can use our 740 mmHg that was given in the problem, right? So this was 740 point mmHg. And so if you do that, you can do the math. You'll notice unit-wise, and this is, again, kind of weird, but you have Kelvin here and Kelvin here. So sorry that Kelvin's written in a weird place. You have moles on top, moles on the bottom of the numerator. And then on the very top, you now have mmHg, which cancels with mmHg down here, and you have liters as your uncanceled unit. And if you plug that in your calculator, you will again get the same value. You will get 6.18 liters because you now have an R value that fits your pressure. So you can do either one. You can always use 0.0821 and always convert into ATM, or you can use the different R values depending on the pressure that's given in the problem. All right, let's try one more. In number 3, we are looking for grams. So remember, grams is not something that we just get in a gas law, but there is one of our units that does relate to grams because we know from the periodic table that we can tell the number of grams in 1 mole of any substance. So with that in mind, if we want how many grams, we really want N. If we know moles, we can get to grams. So we know that we're looking for N. There's a there's a volume that's given, and the volume given is 45,100 milliliters. If you're thinking ahead, all those R values have liters as a unit, so let's take care of that right now. We know that milliliters won't cancel with our R values, so we will need 1,000 milliliters in 1 liter, and we really have 45.1 liters, and that will cancel with our R values, so that's good. It says we have a temperature of 34 degrees Celsius, significant to the ones place. If we add 273.15 to this, we will get 307 Kelvin. Right, so that's our new temperature. We know we need to be in Kelvin, and we've stopped at the 307 because we're significant to the ones place. And then we're told that the pressure is 1.04 ATM. So again, we have a bunch of variables. We've fixed some of them because we know what R value is coming. We know that we need to use PV equals nRT based on the variables that we have. But this time we're solving for N. And so to solve for N by itself, you got to get rid of that RT. So N is going to be equal to PV over RT. Let's plug in what we have. So the pressure given in the problem, so N is equal to the pressure given in the problem, which was 1.04 ATM. We solved for a new volume. It was 45.1 liters. That is over our R value now, which is 0.0821 liters times atmospheres. We're using that one because our pressure is in atmospheres, times over moles times Kelvin, times our temperature, which we said was 307 K. So let's look at our units. Unit-wise, in the very top numerator, we have ATM, and we have ATM in the denominator. We have liters top and bottom as well, and then in the denominator only, you have a Kelvin in the numerator and you have a Kelvin in the denominator. So we cancel everything else, but we're really left with moles, right? But that moles is in the bottom of the denominator. So said another way, if I get rid of all the numbers, unit-wise, I have 1 in the numerator over 1 over moles. Or, said another way, 1 over inverse moles. And how do you get an inverse out of the denominator? Well, you multiply by its reciprocal. So really, and it's easier to see this here, if we want to get this moles out of the denominator, we really multiply it up, and this is the same as 1 over the moles is the same as simply moles in the numerator. So actually, even though moles looks like it's buried deep in the denominator, it's actually in the numerator. So when we solve this, we will get a unit of moles, and it turns out that the number we get with 3 sig figs is 1.86 moles. Remember that the question says that we're dealing with CO2, but it asks for grams. So we have 1.86 moles of our gas. Our gas is CO2. We need to figure out from the periodic table, in 1 mole of CO2, how many grams are there? And you can feel free to calculate the molar mass. We've done that several times this year. When you do that, you will get the molar mass is 44.01 grams of CO2 for every mole. We start with 3 sig figs. We'll end with 3 sig figs. When you do that math, you will get 81.8 grams of CO2. You'll notice conveniently that your moles cancel. You're left with grams. And so at the end of the day, this is our mass of CO2 under those conditions.